last thing I want to talk about at the end of the semester here is gravitational field. So what is gravitational field? So remember that we know that we have the Earth here, right? And if we put a mass right here, its tendency will be to fall. And we already have a pretty good understanding of what of that fall experience if we're on the surface of the Earth, right? Because we know that on the surface of the Earth, if we if we just hold a pin up and we drop it, it will fall and it will have an increase of speed of 9.8 meters per second squared. So how do we know that? Well, we know that the gravitational force that's acting on us, on our mass, causes us to accelerate at gravity. And gravity is really just a ratio of our force, our weight, to our mass. That's what gravity is. And at the surface of the Earth, that ratio of our weight to mass is 9.8 newtons per kilogram. Just means that every kilogram of mass experiences a force of 9.8 newtons, which causes us to accelerate at 9.8 meters per second squared. If we were to go out, we would have less acceleration the further we go out. But regardless, we are always going to be pulled on by some kind of force when we're near the Earth, right? Whether there is a mass there or not. So the gravitational field is this imaginary force field around the Earth or any body of mass. And on the Earth, the strength of the field is 9.8. So we could draw a vector showing that it's 9.8 towards the center of the Earth, newtons per kilogram. And if we were to double the radius, it would be less. And if we were to triple the radius, it would be even less. Well, how can we find out what gravity is, what the gravitational field strength is? So gravitational field and gravity, acceleration of gravity, are the same thing. Any body of mass experiences that. So you can kind of think of gravity as like a warp in space. Imagine that space is like a balloon. You put a heavy ball on the balloon. The balloon would be warped around that heavy mass, that ball. And if you put an object near on that warped area, right, that cone of space, when it's further away, there would be less warping than when it's closer. And so it would speed up as it goes closer to, as it falls down that well, that gravity well. So it turns out that we know two things, that weight is mg. But it's also the gravitational force between the Earth and us, divided by the distance between the Earth and us, right? Which would be, when we're on the surface of the Earth, it would be the radius of the Earth, right? If we're out further, it would be more than that. But those two things are equal to each other. And notice that your mass goes away. That gravitational field is always there, regardless of whether you're there. The units of it are going to be newtons per kilogram or meters per second squared. It's the same thing, but we're going to think about this newtons per kilogram unit right now. So the radius, okay, so let's say we have planet P, and let's say we want to know what its gravitational field is. Well, the first thing we need to know is we need to know the mass of planet P. Let's say the mass of planet P is 3 times 10 to the 27 kilograms. And let's say that the radius of planet P, Okay, so it's radius, right? It's radius. There's the center of it. Let's say that that is 6e to the 19 meters. So if we wanted to find gravity, all we would have to do at that location, right, on the surface of that planet, we would just need to know 6.67 e to the negative 11 newtons meters squared all over a kilogram squared times 3e to the 27 kilograms divided by 6e to the 19 meters squared. So if we put that in our calculator, 6.67 exponent negative 11 times 3 exponent 27 equals, divided by 6e 19 squared in parentheses equals 5.55. Some reason I've got a square root there and I do not want a square root. So let me do that one more time. Sorry about that. 6.67 exponent negative 11 times 3 exponent 27 equals, divided by 6e to the 19 it keeps taking the square root. I don't like that. Okay. Let's do it this way then. 6.67 exponent negative 11 times 3 exponent 27 equals, divided by 6 exponent 19 times 6 exponent 19 in parentheses. There we go. 3.6 e to the 39 newtons per kilogram, which is an extremely crazy number because this is a very, very small planet that's very, very dense. So it's a very, very dense planet. Let's say that we wanted to look at a different planet. Okay, so why don't we talk about the Earth? Well, we already know that gravity is 9.8. So let's also talk about that relationship. Gravity is equal to big G times the mass of the Earth all over the radius between you and the Earth squared. So let's talk about that. When you're on the surface of the Earth, it's just the radius of the Earth, right? What if you double that radius? Okay, so now there's another double. So that's 2RE. If you do that, G is proportional to 1 over R squared. So it's just like with weight. If I double R, my gravity will be 1/4 as much. If I triple R, my gravity will be 1/9 as much. If I cut my R in half, then my gravity will be 4 times as much. So let's round this to 10 to make it something easy. So if I was at a location twice the radius of the Earth, the gravity at that location would be 1/4 as much, which would be 10 over 4, right? Or 5/2, or 2.5 meters per second squared. And if I cut my radius in half, the inverse of that would be 2 squared would be 4 times 10, which would be 40 meters per second squared, which means that I would weigh 4 times as much at that location.